This is the video for Algebra 1, Chapter 9, Section 1, which is called Properties of Radicals. If you are taking paper notes, please go ahead and pause the video whenever you need to finish writing. First off, using properties of radicals. So a radical expression is an expression that contains something called a radical. You might know it as the square root symbol, but really the name of it is the radical symbol. An expression involving a radical with an index of n is in simplest form when these three conditions are met. So no radicands have perfect nth powers as factors other than 1. No radicands contain fractions, and no radicals appear in the denominator of a fraction. Going back here, index n, remember an index refers to the little number to the left of the symbol. We have talked about that before. In a square root, that index is a 2. All right. We've also done a lot of cubed roots where the index is 3. Okay. Now the radicand has perfect nth powers other than 1. Radicand is the number inside the symbol, and this is like basically the how you know something is simplified as much as it can. Okay, and then you can't have a radical in the bottom. So on this very bottom, there is a listing of the product property of square roots. Notice I would just kind of look at the numbers one in the middle. If you do have something like the square root of 9 times 5, which would be 45, but you could break that into the square root of 9 times the square root of 5. And because we know the square root of 9 is 3, that becomes 3 times the square root of 5. You'll also hear people say 3 radical 5. Okay? All right, so now we're going to go over 2 examples. One is simplifying the square root of 108. So first off, you should factor that, keeping in mind that you want to find the largest factor of 108 that is also a perfect square. So that would be the number 36. After that, I can break that up into the square root of 36 times the square root of 3. And finally, the square root of 36 is 6. So it becomes 6 radical 3, or 6 times the square root of 3. In my second example here, we do have a variable inside, but let's take a look at what happens there. So that one is going to be broken up into 9 times x squared times x. And the x's are broken up because x squared is a perfect square, but x by itself is not. So the square root of 9, okay, first they went ahead and broke those 3 apart. Then the square root of 9 is 3. The square root of x squared is x. But I can't do anything with the square root of x. So that stays all by itself.
The square root of 3. Part B, the square root of 25x to the 5th power. First factor using the greatest perfect square factor. The greatest perfect square factor of x to the 5th power is x to the 4th power. So the square root of 25x to the 5th power equals the square root of the quantity 25 times x to the 4th power times x. Next, use the product property of square roots to get the square root of 25 times the square root of x to the 4th power times the square root of x. Because the square root of 25 equals 5 and the square root of x to the 4th power equals x squared, The expression simplifies to 5x squared times the square root of x. Simplify each expression.
All right, now we're going to move on to the quotient property. So very similar to what we just did with multiplication and the product property. But this time, if you notice, it's basically saying if you have a fraction like 3 over 4, which remember is a division problem, 3 divided by 4. You can break that into the square root of 3 divided by the square root of 4, and then you can go ahead and simplify the bottom. So we'll do a couple examples here. First one, I have the square root of 15 over 64. And on this one, I go ahead and break it into the square root of 15 over the square root of 64. And since I know the square root of 64 is 8, there is my answer, and I can just leave it like that. I do not have to put it into decimal form or use a calculator. For the next one, I have the square root of AB1 over x squared. I'm going to break that into two parts, and they are both perfect squares. I can take the square root of the top and bottom. So my answer would just become 9 over x. Next, I'm going to show you another video with 2 more examples.
Simplify each expression. Part A, the square root of the quantity 11 divided by 36. First, use the quotient property of square roots. The quotient property of square roots says that the square root of a quotient equals the quotient of the square roots of the numerator and the denominator. So the square root of the quantity 11 divided by 36 equals the square root of 11 divided by the square root of 36. Because the square root of 36 equals 6, the expression simplifies to the square root of 11 divided by 6. Part B, the square root of the quantity 144 divided by n squared. First, use the quotient property of square roots. The square root of the quantity 144 divided by n squared equals the square root of 144 divided by the square root of n squared. Because the square root of 144 equals 12 and the square root of n squared equals n, the expression simplifies to 12 divided by n. Simplify.
Okay, moving on to the last part here, it says you can extend what we just did with the product and quotient properties of just square roots to other radicals, such as cubed roots. Okay, so we're moving into cubed roots now. So the index would be a 3. When using these properties of cubed roots, the radicands may contain negative numbers. They couldn't do that before, for example, because you can't take the square root of negative 9, because there aren't two numbers multiplied together that would be negative 9. 3 times 3 is 9, but negative 3 times negative 3 is still positive 9. But once you have a cubed root, let's say you have the cubed root of negative 8, you could say 2 times 2 times 2 is positive 8, but negative 2 times negative 2 times negative 2 is negative 8. So let's do a couple, actually I have 4 examples here. First one, I have the cubed root of 128. Notice the little 3 right there. So I want a number times itself 3 times that's negative 128. So first off, I would factor that using the greatest possible perfect cube factor. Okay, so of that, I know that there isn't a number times itself 3 times that's 128, but there is a number 3 times itself that's 64. So I'm going to factor this into negative 64 times 2. From there, I can split those up like you see, and then write that as negative 4, because negative 4 times negative 4 is positive 16, but if you multiply by another negative 4, you've got negative 64. So there is your result. On the next one, this time I have the cubed root of 125 times x to the 7th. Now in this particular one, there is a number times itself 3 times that is 125. So I'm just going to leave that as 125 times x to the 6th times x. And I'm going to put the x to the 6th right there because that is really going to be 2 groups of 3. So look what happens here. After I break it up, that x to the sixth, that's 6 x's. That means I have 2 groups of 3, so that's what can come out of the radicand. But left behind is the cubed root of x. I can't do anything with it. I would need 2 more x's on the inside to take another group out. So in the upper right, I'm going to go ahead and break that into 2 problems, or actually not 2 problems, but let's see, a radicand divided by a radicand. Let's say it that way. Okay. Now I can't do anything with the top. It's just like the one down here. I only have 1 y. To get rid of the radicand, I would need 3 y's in there, but I don't have that. So I just have to look at the bottom. Now on the bottom, there's actually, well, the number 6. 6 times 6 is 36, and multiply it times 6 a third time, and you do get 216. So that would be your answer there. Now for the last one here, take a look at those numbers. I've got an 8 and a 27. So first off, we're going to break that into 2 different parts, the top and bottom there. Then the number 8 is a perfect cube. So is x to the third, but I'm going to have a leftover x. Now the 27 is also a perfect cube, so I can leave that one alone. And y to the third is a perfect cube. So you can see them all separated now. I sometimes skip showing this part if I'm working these out. But 2 times 2 times 2 is 8. And there's 1 group of 3 x's I can take out. The other x stays alone. 3 times 3 times 3 is 27, so a 3 comes out, and then there's 1 group of y's that I can take out.
Simplify each expression. Part A, the cube root of 135. First factor using the greatest perfect cube factor. The greatest perfect cube factor of 135 is 27. So the cube root of 135 equals the cube root of the quantity 27 times 5. Next, use the product property of cube roots to rewrite the expression as the cube root of 27 times the cube root of 5. Because the cube root of 27 equals 3, the expression simplifies to 3 times the cube root of 5. Part B, the cube root of 8x to the 4th power. First factor using the greatest perfect cube factor. The greatest perfect cube factor of x to the 4th power is x cubed. So the cube root of 8x to the 4th power equals the cube root of the quantity 8 times x cubed times x. Next, use the product property of cube roots to rewrite the expression as the cube root of 8 times the cube root of x cubed times the cube root of x. Because the cube root of 8 equals 2 and the cube root of x cubed equals x, the expression simplifies to 2x times the cube root of x. Part C, the cube root of the quantity n squared divided by negative 1000. First, use the quotient property of square roots. The cube root of the quantity n squared divided by negative 1000 equals the cube root of n squared divided by the cube root of negative 1000. Because the cube root of negative 1000 equals negative 10, the expression simplifies to negative the cube root of n squared divided by 10. Part D, the cube root of the quantity 343a to the 8th power divided by b cubed. First, use the quotient property of cube roots. The cube root of the quantity 343a to the 8th power divided by b cubed equals the cube root of 343a to the 8th power divided by the cube root of b cubed. Next factor using the greatest perfect cube factor. The greatest perfect cube factor of a to the 8th power is a to the 6th power. So the expression can be rewritten as the cube root of the quantity 343 times a to the 6th power times a squared divided by the cube root of b cubed. Then use the product property of cube roots to rewrite the numerator as the cube root of 343 times the cube root of a to the 6th power times the cube root of a squared. Because the cube root of 343 equals 7, the cube root of a to the 6th power equals a squared, and the cube root of b cubed equals b, the expression simplifies to 7a squared times the cube root of a squared divided by b.
All right, if any of the videos were hard to hear, remember you can also pull up the slide deck on your own and play them. After this is all done, you'd want to go to the assignment, and I'm pulling that up right here, and there's 12 problems. Keep in mind when you do those, you may have to use the symbols over here, but that's